Hello, everyone. This is the lecture for section 3.5, the derivative of trigonometric functions. What you guys are going to see in the next couple sections until the end of chapter 3 is that these sections are going to go through very quickly. We're just going to keep stacking rules on top of rules on top of rules. Basically, we're stacking more and more shortcuts for how to find derivatives. Okay. The next one up is section 3.5. Derivative of trigonometric functions. So section 3.1, 3.2, we learned how to sort of construct and define a derivative using that limit definition. Section 3.3, we learned our first couple of shortcuts. Section 3.4, we started to throw it into some natural and social sciences and physical sciences applications in there, okay? At this point, we're just gonna start stacking on more and more and more rules, okay? So in section 3.5, trig functions. How do you take the derivative of those, okay? There's the list that's right there. The two big ones are these two right here. The derivative of sine and the derivative of cosine, okay? All the other ones, you could memorize them, but they are easily proven using the two in yellow. Okay, and that's actually what I'm going to make you guys do in the lecture questions. I'm going to have you guys prove them. Okay, you can remember them just as you see them here. And that's fine, perfectly fine. The way that I like to do it is this. I'm going to put it in the hot pink right here. Sine, cosine, like that, and then like this. Okay, and then there's a plus here. Actually, I'm going to put it on the inside. Plus here, and then a minus here. Okay. So what ends up happening with if you take continued derivatives of sines and cosines, okay, the pattern of derivatives just becomes cyclic. That's it. Okay. And here's the reason why I like to do it this way. So the derivative of sine is positive cosine. Okay. And then the derivative of cosine is negative sine, okay? And if you notice, that's what gave me the, the derivative of each one. I just follow the circle wherever I need it to, okay? So if I get the derivative of negative cosine, that's gonna be the negative of a negative sine, so it's gonna be positive sine. You guys see how that works, okay? And on my tests, back in my day when I was doing calculus, I'd have this thing at the very top of my page. And then I just circled whichever direction. It'll be even more useful when you get to Calc 2, when you have to learn about integrals. The circle goes backwards, okay? So anyway, let's go ahead and do an example. Okay, so at this point, we know some of the shortcut rules, right, for how to take a derivative, okay? That's exactly what we're gonna use here. Okay, but now we get sines and cosines. So let's go ahead and just take the derivative. This is a quotient, so that means this is going to be a high divided by a low. So if my high is 1 plus sine of x, right, and my low is x plus cosine of x, right, then the derivative of the high, that's going to be, let's go back to my circle there. There we go. The derivative of sine is just cosine, so it's just going to be cosine, right? And if that's my low, the derivative of the low is going to be 1. The derivative of cosine is negative sine, so 1 minus sine of x, right? And if we want to take the derivative of this, right, then f prime of x, right? You guys remember the little saying, right? It's low times d high minus high times d low all over low squared. Let me draw that nice. Low squared. So f prime of x in this case, right? We just get to follow the rule. So low x plus cosine of x times d high times cosine x, okay? Minus high, 1 plus sine of x, right? D low, 1 minus sine of x over low squared. So the low is x plus cosine of x quantity squared, okay? So all of this is going to test your trig very, very, very deeply, okay? In many cases, some of these problems, if you use trig on them, you can reduce them to something much simpler. So that's what I'm going to do with this one. If you don't have a trig sort of refresher page, if you look to the to the right of this problem, I put a trig trifold, a trig pamphlet that you guys can print out and to refresh your trigonometric identities, basically. Okay, so let's go ahead and simplify this. Okay, so this is going to be equal to, I'm going to put it down here, is going to be equal to x cosine of x plus cosine squared x. And then I'm going to do this distribution. If you do this distribution correctly, you're going to get 1 minus sine squared of x all over x plus cosine of x quantity squared, okay? This thing right here, that is equal to cosine of x. So that's one of the Pythagorean identities. So x cosine of x plus cosine squared of x minus cosine squared of x all over x plus cosine of x squared. You guys haven't noticed yet, you have a negative one here, a positive one there, so this cancels out to x cosine of x all over x plus cosine of x quantity squared. And we are done. Here's our final derivative. Okay, so notice the only new thing that we learned here is the derivatives of sines and cosines. Okay, that's it. The rules sort of work out the same way. For all the other ones, if you have the derivative of tangent, that's just secant squared. Okay. What comes up next here is quick checks. So part 1 of this quick check is just find the derivative, okay? Find the equation for the derivative, okay? And it turns out part 2 is find the equation of the tangent line at x equal 4, pi over 4, okay? So in part 1, you find the derivative, you get to use the derivative to find the equation of the tangent line in the next section, okay? So again, we can apply this stuff directly to some good old physics, okay? And that's exactly what we're going to do here. So suppose you have a mass on a spring. So this is the chapter in physics that you guys will see this in is what's called simple harmonic motion. So suppose you had a nice little mass on a spring. So here's our spring, okay? It has a nice little mass on it, okay? And it is bouncing up and down, and it's modeled by this function right here, 3 sine t, where t is measured in seconds, and s of t is given in gives the position in inches. Okay. First of all, what we're going to do is just find and interpret s of pi over 2. Okay, so we know pi over 2 is about 1.57 seconds, right? But we're going to go ahead and use s of pi over 2. We're actually going to use the value of pi over 2. So s of pi over 2, that's going to be 3 times sine of pi over 2. Okay? If you guys remember what sine of pi over 2 is, that's 1. So this is going to be 3 times 1, 3 feet. Sorry, inches. Okay. So in physics, when okay, there we go. In physics, we call sort of like, suppose you just let it hang there. Okay. This is what we call equilibrium. Okay. Okay. This point right here is equilibrium. Okay. And in physics, what we do is if it's positive, it moved up that way. And if it's negative, it's down below the point of equilibrium. Okay. Since this is positive, we know it's somewhere up here. Okay. So then this says, right, at t is equal to pi over 2 seconds, right? The mass is 3 inches above equilibrium. Okay. So now comes the next thing. Find and interpret s prime of pi over 2. Okay, so we know what s does. S is the position, right? So s prime is the rate of change in the position. We know that this is a velocity. So this is equivalent to finding v of pi over 2. We're talking about a velocity here, right? So now we get to do s prime of t, right? We need to take the derivative of our thing in yellow that's over there in the corner. So that's going to be 3 times the derivative of sine is cosine of t. So s prime of pi over 2 is 3 times cosine pi over 2. 3 times, if you guys remember what cosine of pi over 2 is, that's 0. So velocity at pi over 2 is equal to 0, right? So at t is equal to pi over 2 seconds, the mass is moving at 0 inches per second, aka it's not moving at all. Okay, so what does that mean in our problem, right? That means that our, I'm going to redraw the little picture for it. Okay, so at pi over 2 seconds, I'm going to do at t equal pi over 2 seconds. We have our little mass, right? It's on a spring. Here's a little spring, here's a little mass. Okay, equilibrium for this thing is down here. Okay, it has been displaced by 3 inches. That's what we got for part A, right? And then part B is telling us that it's not moving anywhere. Okay, so if you think about it, right? If it moved to that point, the velocity was positive, it was moving upward, right? And then same definition, if it's dropping, the velocity is going to be moving downward, right? The velocity is going to be negative, right? Since our velocity is 0, okay, this means right here that our mass that's bouncing on a spring has reached its tippy top and it's starting to come back down, okay? So whenever we study simple harmonic motion, whenever there's something that happens repetitively, okay, that's where we get to see a lot of these derivatives with sines and cosines in it, okay? I think that is it for this section because lecture questions come up right after this. So this concludes the lecture for section 3.5, I believe, 3.5, right? Yeah, 3.5. Okay, if there are any questions about this material, please stop by my office hours or my drop-in hours, or you can guys come to the math lab or send me an email or shout at me through a discussion. I check them every day, okay? Besides that, I'll see you guys around.